On the morning of June 30th, 1908, a fireball ripped through the sky over the Siberian taiga. Moments later, it detonated with the force of a 15-megaton TNT explosion. Evenki herders living in the region described a blinding flash, a wall of searing heat that singed their clothing, and a shockwave that physically hurled them and their animals through the air. The blast registered on seismographs across the globe as a 5.0 magnitude earthquake, and barometers as far away as Great Britain recorded pressure waves circling the Earth for the next several days. An event of this magnitude, releasing 1,000 times more energy than the Hiroshima bomb, should have left a massive, permanent scar on the Earth's surface. But the site was so remote it took nearly 2 decades for a scientific expedition to arrive. In 1927, Russian mineralogist Leonid Kulik trekked into the swampy epicenter expecting to find a massive impact crater. Instead, he found 830 square miles of total destruction. Millions of trees had been flattened, all of them pointing away from the center of the blast. At the very center, the evidence was even more confusing. The trees there were still standing upright, but they were stripped of their branches and bark, left looking like scorched telegraph poles. There was no crater. Kulik searched the area extensively but found 0 meteor fragments, only the footprint of a colossal energy release. This lack of physical evidence invited decades of speculation, with theories ranging from antimatter collisions to miniature black holes. Without a crater or debris, researchers lacked a clear explanation for how an explosion this size could occur without a direct impact. Modern fluid dynamics finally solved the puzzle. The asteroid never struck the ground because it was destroyed by an airburst. The incoming object was a stony asteroid, roughly 50 to 80 meters across, entering the atmosphere at a velocity of up to 20 kilometers per second. At that speed, the air itself becomes an obstacle, creating an extreme pressure gradient. High-pressure air stacks against the front, while a vacuum trails behind. Purdue University researchers found this air doesn't just push the asteroid, it actively infiltrates the rock's microscopic cracks. This causes the asteroid to shatter and vaporize in midair. Within seconds, it converts all its kinetic energy into an aerial bomb. Our atmosphere acts as a crushing shield. It destroys smaller asteroids before they reach the surface, but in doing so, it transforms them into massive explosions miles above the ground. This aerial detonation explains Kulik's telegraph-pole trees. A shockwave hitting the forest directly overhead strips branches without toppling the trunks. Simultaneously, the wave moves horizontally, creating the 830 square mile butterfly-shaped pattern of felled trees miles from the center. We saw this same mechanism in action in 2013 when an asteroid exploded over Chelyabinsk, Russia. That blast injured over 1,600 people, mostly from windows blown out by the shockwave. The Chelyabinsk event was small compared to Tunguska, but it confirmed a dangerous reality. Mid-sized asteroids can trigger megaton-scale explosions over populated areas without ever leaving a crater. For years, planetary defense focused on giant extinction-level impactors, but Tunguska-sized objects are much more common, occurring roughly once every few centuries. These threats are difficult to track. At 50 to 100 meters, these dark, stony objects are easily missed by optical telescopes against the blackness of space. Modern defense now relies on infrared surveys like NEOWISE, which detect the heat signatures of these asteroids rather than just their reflected light. This shift in observation expanded our understanding of cosmic risks. It proved that the atmosphere can act as a detonator just as easily as it acts as a shield. To manage this, NASA established the Planetary Defense Coordination Office. Their mission is to track these objects and develop ways to intervene before they reach our atmosphere. One method is the kinetic impactor. In 2022, the DART mission collided a spacecraft with an asteroid to see if we could shift its trajectory. The mission was a success, proving that we can alter the orbital mechanics of a distant rock. Tunguska was a 15-megaton warning, but because we now understand the mechanics of the airburst, we have the tools to predict and prevent these events before they happen.